Ladies and gentlemen, I'm Yan Chen. I am Professor Chin-Chih Chang from Technical University from Taiwan. It's our pleasure to show our paper with you. Today, our topic is Optimal Preventive Replacement Policy for a System with Mission Durations. First, we introduce the prefix. For the mission-oriented system, it is not feasible to do any preventive replacement when a mission arrives at random time and lasts for a duration. If the decision maker abort the mission and shut down the system for preventive replacement, it will cause a huge economic losses due to the failed missions. The typical example often occurs in many mission-critical systems, such as emergency communication system, enterprise database, and production equipment. So it is a great important to plan operate preventive replacement policy with mission duration, as the reliability is required at mission time, and no replacement can be done preventively during the mission duration. Okay, in this paper, we propose an age replacement policy for a deteriorated system with mission duration, and derive the optimal mission duration and optimal preventive replacement time. Now we present our system model. First, we consider a new system with value time x has general distribution function f of t and a probability density function f of t. Then the instant value rate of the system is RT, which is f of t divided by f bar of t, when f bar of t is the survival function. And we consider the system should keep the operating state at mission arrival time y for a duration y to y plus d. When y has a general distribution function g of t with probability density function g of t and a survival function g bar of t. Note that d is considered as a mission duration, during which the system should provide reliability and no preventive replacement, which we call PR, can be implemented. Suppose that the system experienced one of the two types of value. One is type 1 value, which is minor with probability q and is corrected by minima repair. And 2, the type 2 value, which is catastrophic with probability p. P is equals to 1 minus q. And the p requires the type 2 value requires a corrected maintenance CR. Let Z be the arrival time until the first type 2 value, where Z has a distribution function FZT and a probability density function FZT, a survival function Z bar T. The various costs divided are as follow in our model. The C1 is PR cost, C2 is CR cost, and CM is a minimal repair cost. This slide we present the basic preventive replacement we call BPR. For BPR policy with a mission duration D, a PR is only planned to immediately at time Y plus D if no type 2 value occurs before the mission arrival time Y. And in the other hand, the system undergoes minimal repair instantly at each type 1 value and immediately and it is planned a CR at the first type 2 value before time Y plus D. And we show the situation like these two figures. Please refer to it. And the mean cost rate function for a BPR policy can be obtained as the following: CB of D. To minimize the CB of D with respect to D, we can differentiate CBD with respect to TD and setting it equals to 0. Then the optimal mission duration D star can be determined uniquely. Okay, this slide we present the preventive replacement first. We call the PRF policy. For PRF policy with a mission duration D, a PR is only planned to immediately at the planned time T or time Y plus D, whichever occurs first. And the system is implement a PR at time Y plus D even through T is planned during Y, the interval Y to Y plus D. And the mission duration D can be predetermined by the optimum BPR policy, and the system undergoes minimal repair instantly at each time 1 value and implement at a CR at the first type 2 value before time Y plus D or time T. And we show the fourth replacement state in these figures. Please refer to it, the state 1, 2, 3, and 4. Okay. Now we optimal the PR time T star of F, and the mean cost rate function for PRF policy can be obtained as the following equation, which is we called CFT. And to minimize CFT with respect to T, we can differentiate CFT with respect to T and setting it to equal to 0. Then the optimal PRT time TF star can be determined uniquely. This slide we offer the numerical example to show our finding. Consider the system value time x is a variable distribution f of t like this, and the mission arrival time t y is exponential distribution g of t like this. The following data are used for the parameters. Alpha is equal to 1, beta is equal to 2, theta is 1, and C1 is 500, and C2 is 1000, and Cm is 100. And we can find finally in this table the optimal BRP policy and PRF policy and their minimum repair, minimum mean cost rate. Is in the following table, and in this table we can find similar to our anticipated result. Table 1 shows existent and finite and unique optimal solution for each PR policy. When the minimum repair probability Q increased, and we can find the minimal mean cost rate decline, and the optimal mission duration D star, PR time TF star increase. And it is institutive because the lower probability of major value result in a length PR schedule. That's all. This is the end of our presentation, and thank you for your listening.